and we will begin discussing the sun. Okay. I didn't have you guys get your clickers, so if we get to a clicker question, why don't we just take a minute now and get your clickers, and then that way you'll have them. So now this will be on your recording. Everybody marching up to get the clickers. Clearly I didn't plan this quite optimally, but nevertheless, it's a small class, so we've all got our clickers. We can proceed. Okay, so the sun is obviously, let me adjust the lights a little, the closest star to us, as we discussed last time. You know, that's kind of a bit of a trick question sometimes. I don't know why it's asking me that. I probably should have clicked the bottom one. Anyway, so the sun is the closest star to us. Sometimes that's a trick question people ask. You know, where's the closest star? And people are thinking Proxima Centauri or Alpha Centauri, but really it's the sun. That said, the sun is still 93 million miles away from us, which in our everyday lives seems like a great distance, but of course in astronomical scales, that's not really that far. And again, similarly, compared to the size of the Earth, the sun is immense, but then again, compared to other stars, not necessarily that big. For us, to give you some scale, compared to the Earth, 1 million Earths would fit inside the volume of the sun. I think I mentioned that last time. And the amount of energy that's being released is the same as if you had, I'm going to have to tell this to be quiet. All right. Would be the same as if you were setting off atomic bombs at the rate of 100 billion every second. So that's like hard to even conceptualize, I think. Suffice to say, an enormous amount of energy is being produced by the sun every second. Okay, and so, you know, a natural question would be, well, why doesn't it just blow apart then if there's all this energy that's equivalent to bombs going off? And that has to do with the fact that it is so massive that its gravity is holding it together, right? There is outward pressure from all the release of energy, but there's also inward attraction because it's such a massive object. So that balance between gravity pulling in and pressure pushing out is the state of equilibrium that our sun finds itself in at this current moment. Okay. If you look real closely at the surface of the sun, it's not just a nice yellow surface as you might see here with a couple sunspots. Really what it is that the surface itself is granulated. And those granules are actually really large. You see here the scale mentions 10,000 kilometers across. So, you know, it kind of just looks like bubbly soup almost if you're looking at it in this picture, but bear in mind that these are huge grains or granules that we are seeing. They correspond to regions where we have hot gas rising or cool gas sinking within the surface of the sun. This quote-unquote surface is not like a solid surface like the surface of the Earth, but we call it a surface because that's the part that we actually see as an opaque thing. And this surface is also known as the photosphere. Okay, there's a lot of information here on this table, and you're not going to be held responsible for knowing all of this information. So let me just highlight some of the important things. We talked about the distance at the top here, 93 million miles away. That's also known as 1 astronomical unit, or 1 AU. So that's kind of an important number to bear in mind. You don't have to necessarily memorize 93 million miles. It's nice to know, but you know, the 1 AU you should know. That's how far the sun is from us. And you know, to the right, these are methods that have been used to verify these things. So, you can use radar or triangulation to verify these numbers. We don't really need to worry too much about the radius or mass of the Earth, just kind of to give you a sense of scale. They're listed here, and also to just maybe compare a little bit to other stars when we get to them. That this sun is really massive and large, but compared to other stars, not so much. Its average density isn't terribly important for you to know that number either, except that, again, in relation to a rocky world like the Earth, that's a lot less dense than what the Earth is. So even though the sun is more massive and much larger, it's less dense. And that's because it's made out of gases rather than rocks like the Earth. Okay, once you go inside, though, it gets pretty dense because everything is being attracted and pulled to the center gravitationally. And so that's why you're seeing such a difference in temperature here as well. You go from millions of degrees at the core to about 5,800 degrees on the surface. 5,800 degrees is probably a good number to know. Again, I'm not going to make you memorize any of this stuff, but in the back of your mind, it's good to kind of keep that in mind. And you don't need to know 15 million Kelvin. Millions of degrees is really the thing to bear in mind. Again, just in relation to other things, having some sense of scale here. What the sun is made of, this is kind of important. The first two things anyway, hydrogen and helium, that's pretty much what most stars are made out of, hydrogen and helium. There are some exceptions, as we're going to see towards the end of stars' lives, when you have what we call stellar corpses. But most stars that are in the prime of their lives are made up of mostly hydrogen and a little bit of helium, and sometimes a smattering of other things. As you can see, everything else only makes up about 2% of the sun's composition. So when we're looking at spectrum of stars and we see that there are lines corresponding to, say, calcium, that amount is still only a tiny fraction of what the sun is made out of. The amount of luminosity, remember we talked about it being a wattage, right? I said if you know the luminosity, it's like a wattage of that star. So it's like if you have a light bulb and it's a 60-watt light bulb, it's going to appear a certain brightness to you, but if you move it farther away, it might be dimmer. Knowing what the absolute wattage is of the sun helps us determine, how bright actually is it? How does that distance scale with the brightness? And then that can help us deduce things about other stars. But again, not a number that you need to memorize. Okay, so we talked about the photosphere already. Let me just move this thing over. Oh, question.
Yeah, if you go back.
Yeah. Oops, hold on, it's not responding.
Yep.
Yeah.
Okay, so when you measure the light intensity of a light bulb, it's actually measured in lumens, isn't it? So why wouldn't we use lumens for the luminosity of astronomical units?
I believe it's just a different set of units. And when you buy, so maybe, is that a compact fluorescent that's measured in lumens? Because I know, if you buy an incandescent bulb, it'll say 60 watts or 45 watts or something.
You replace those light bulbs with the spiral ones or whatever.
The compact fluorescents, yeah.
It measures of lumens.
Oh, that's interesting. Okay, I think I just didn't know that. But I think it's just another set of units.
Now that I think about it, I can't remember if lumens is the color of the light, because you
Oh.
can have a pure white light bulb, which might be a certain.
Yeah.
I can't
I'm not terribly sure on that, actually. But if it is a measure of luminosity, then it's simply just, lumens would be just a different unit that's chosen, kind of like how I could tell you the distance to the sun either in AU or kilometers or miles. And so I think astronomers have just traditionally used watts. But yeah, I'm sure you could, if it is a measure of luminosity indeed, then you could figure out what that is equivalent to in lumens. Okay. So moving on, the photosphere we've already mentioned is the surface, quote unquote, that we actually see. It's the part that's opaque and yellow and looks kind of like a yellow ball in the sky. And again, it's not a hard surface, it's not a solid surface, everything is gaseous, but it's what we actually see. And it's not like a single layer in the sense that it's like a tiny amount of thickness. There is some thickness to it. Of course, in the size relationship to the sun itself, that actually probably is kind of tiny, but 500 kilometers thick is actually what we're talking about in terms of how thick the photosphere is. So you could almost think of it like a shell around the surface, but it's not really a hard shell. It's just the opaque, quote-unquote, shell or surface that we see. This is the part that's almost 5,800 Kelvin. Okay, and that, as we're going to see, is characteristic of a star like the sun. And I mentioned before that it's in this balance between gravitational forces, which are pulling in on it, and pressure forces from the outward flow of energy. And so at this point in the sun's life, it's existing in a sort of equilibrium between those two forces that would seek to either crush it down into a point or explode it out into space. It's sort of like, balanced. Now, the sun's lifetime is expected to be overall 10-ish billion years, and we're about 4.5-ish billion years into that. So we're about halfway through its lifespan, and it should exist for another 5-6 billion years. Okay? If you did a cutaway of the interior of the sun, as you make your way to deeper and deeper parts of the sun, you're going to notice a few things. First thing, I want to look at the thing on the right first. The first thing you'll notice is the density increases as you go in towards the core of the sun. And we've already explained that a little bit in terms of, that's where everything is gravitationally attracting to that center. And so you've got like the most dense thing in the center. You'll see that planets do this as well. If you were ever to study planets, of course, I don't know if we'll get to that, like I said before, but basically, the core of the Earth is also more dense than the surface of the Earth. And what's happening is that you can think of it like denser things sinking for the Earth, but for the sun, it's a little bit different because it's gravitational attraction that's really at work here. The other side of this graph is showing you that the temperature is going to increase as you go towards the core of the sun as well. We're going from thousands of degrees to millions of degrees by the time we get to the core. And that's actually, if it wasn't the case that it was millions of degrees in the core, then we couldn't have these fusion reactions that take place in the core and produce the sun's energy. It needs to be that hot, in other words, for these fusion reactions to take place. Or you could think of it in the reverse logic. The fact that there are these fusion reactions taking place means that it must be that hot. Okay, so that's the right-hand picture. On the left-hand side, what you want to take away from this is that there are different methods by which the energy is going to transport, depending on where you are within the sun. So maybe at one point in your past you learned about conduction, convection, radiation. Does that ring a bell as methods of heat transport? Conduction is where you are physically touching something and it feels hot. So if you touched a hot pan and got burned, that was because conduction was taking place right to the surface of your skin. You were in contact with it. Convection is what drives like a forced air heating in your home, where you've got air circulating and hot air rising, cool air falling into the return vent, and then it cycles around and round and warms your home. And radiation is where the energy is just free to spread out, not necessarily in contact with anything, but also not really circulating. So if you were near a campfire and you put your hands very close to it, you're probably feeling the warmth of the fire radiating onto your hands. Okay, so we don't have really much in the way of conduction happening as depicted here, but we do have the other two methods of heat transport going on. Deep near the core, this warmth is radiating out to the outer layers. And the reason for that is that it's really dense here, as the thing on the right shows. So you're not going to effectively be able to get very good convection going on, so it radiates instead from the core. And then when you get to the outer layers and it's a little more diffuse, then we can have some convection currents circulating around. And when we're looking at the photosphere, that's kind of what we're seeing. When you're seeing those hot gases rises and cool gases fall, bubbling up, that's a sign that this convection current is taking place closer to the surface of the sun. Oh, and once the energy leaves the sun, there's only one method by which it can be transported from the surface of the sun to us, and that's radiation, because convection relies on the existence of gases, and in the vacuum of outer space there are no gases, right? It's just empty, so you can't have convection, and clearly we can't have conduction because we're not physically touching the sun. So the only way we get that energy to us is through radiation. It radiates out into space once it's escaped the surface of the sun. Okay, so this is a little bit of a confusing picture here, so I don't want you to I'm not going to dwell on it too much, but we said earlier that the sun is in this state of equilibrium between gravity pulling in and pressure pushing out, and that's true, but it's also helpful to look at it in terms of layer by layer, because that balance, when you're near the surface of the sun, you're not going to have quite as strong a force of gravity or quite as strong an outward pressure force, because you're not as dense there, you're not as hot there, and so the pressure and radiation are in balance at that particular point, but they are not the same amounts as when you're deeper in towards the core of the sun. So deeper in towards the core of the sun, it's denser and more, and so you've got stronger gravity here, but you've also got stronger outward pressure because it's hotter. Okay, so think of it almost like layer by layer. If you just randomly picked a layer at that radius from the center, that particular shell, so to speak, would be in equilibrium. Okay, now the ideal gas law is one way in which we could look at this. I don't know that it's really all that helpful, because in reality, it's not really an ideal gas. An ideal gas is supposed to be really diffuse, and in the sun, it's clearly not. Nevertheless, if you use the ideal gas law, you actually get a decent approximation. So you may remember, if you ever took chemistry class, like PV equals NKT or nRT, depending on which constant you use. And so you can solve that equation a little bit differently and relate the pressure to whatever that constant is, times temperature and density. But it's basically saying that as the temperature and density increase, the pressure is going to increase. And so that kind of explains this outward pressure arrow. Okay, so we mentioned that near the surface of the sun, just beneath this photosphere, we have convection taking place. And so these convection currents are rising hot gas up, and then cool gas is sinking down, and as that cool gas gets closer to the interior of the sun, it warms up and then rises again, and the cycle just repeats. But if you go deeper into the sun, then you're dealing with radiation. It's so dense there that you're just dealing with basically a radiating zone, and it's really not that effective, believe it or not. It's difficult for a single photon to make its way from the core of the sun out to the surface. In fact, it takes 100,000 years on average for a single photon to go from the core of the sun to the surface and escape. And that's a rather long time, and it has to do with the fact that it's so dense in the interior of the sun that what's basically happening is the photon slamming off of this and slamming off of this, and it's really unable to proceed forward very easily. Has anyone ever been to a really crowded concert or sporting event, and you're just kind of stuck in this crowd, and you're like inching along, and you want to get to the exit of Consol or something, but you're just bumping into this person and that person, and you can't go any faster than that. That's basically what's happening with this photon. It's sort of trapped in this really dense thing with everything around it. It's unable to really make a direct path from the core out to the surface. So when you see the light of the sun, that photon actually left the core of the earth, or I'm sorry, the core of the sun, more than 100,000 years ago. That said, once it makes it to the surface of the sun, then nothing is impeding it, right? Now it's just a vacuum of space. There's nothing in my way if I'm a photon. So when I leave, if I'm a photon leaving the surface of the sun, it only takes me 8 minutes to reach the earth, after I just spent 100,000 years trying to escape the interior of the sun, which is crazy when you think about it, but that's how it works. Okay, now outside of the photosphere that we see, there's a couple other layers that scientists have identified. One is called, the regions above that, we kind of generically call the atmosphere, but one of those layers is called the chromosphere. And that's just the layer just above the photosphere, and then beyond that we have the corona. These layers are difficult to see except when you have a solar eclipse. Then when you're blocking out the rest of the light of the sun, you can kind of see these other layers here. Okay, the chromosphere, if anybody is familiar with this prefix chrome, I think it means colorful, like monochromatic means one color, right? So chromo has to do with colors. So you're going to see these like colorful things sticking out. And the corona, on the other hand, is more of the white wispy stuff that you see beyond that. Okay, here's a better picture of the corona. And again, this I think was either taken during a solar eclipse or purposely the sun was blocked out so that you can see that, because it's so thin that you wouldn't really notice it in the blinding glare of the sun itself. Okay, but this is where our quote-unquote space weather comes from. When you have flares or coronal mass ejections, they're coming from this layer of the sun that's really the sun's atmosphere. And solar flares are releasing energy into space, whereas coronal mass ejections are shooting out great quantities of mass out into space. And those things can affect satellite navigation. I read an interesting article, though, over the weekend saying that something about very, very low frequency radiation that's used in like naval purposes for, I guess, communication or something, has effectively created somewhat of a shield around the Earth. And so we've almost like made this man-made shield from charged particles so that when we do have solar flares and things of that nature, maybe it doesn't affect our satellites as much as you might expect. So that I found to be fascinating, that we inadvertently are protecting our satellites from potentially harmful adverse effects. What's also interesting is that the sun's surface does not sit still, somewhat like how the Earth's surface does not sit still. We've got plate tectonics, which you're probably aware of, and we've got seismic activity that takes place, earthquakes and such. So there are similar effects on the sun that we could call sunquakes. We call it seismology here on the Earth, but to distinguish that we're talking about the sun, we might call that helioseismology, this prefix helio from the Greek god Helios. Is that Greek or Roman? I get them all mixed up. Anybody know? Helios? I don't know. It was some god of the sun. Anyway, that prefix indicates that we're talking about the sun's seismological activity rather than the Earth's. And so you've got layers that are sort of quaking or shaking, similar to how you have on the Earth. Okay, so we've got our first clicker question of the day. Oops, I'm just going to stick that there. Take your time. right, we all in? I feel like we're playing apples to apples. Everybody got their card in? Okay. All right, so let's see what we put. Everybody put A. Yay, you guys got it. So let me just record that. Okay, and so yes, we talked about, and I showed you that schematic that showed at every layer, you've got the inward force of gravity balancing that outward force of pressure. So, some of these other things we haven't really discussed, but, if we haven't discussed them, probably isn't so. Fusion does depend on temperature. I did mention that we wouldn't have that fusion if it wasn't that hot in the core. So we need that hot temperature in the core. Mass is converted into energy. Well, that's true. We probably are all aware of Einstein's equation, E equals mc squared, but that doesn't explain the stability of the star, right? Because that could also be used for atomic bomb purposes, right? And that's a clearly unstable situation. We do have radiation and convection, but they don't necessarily need to balance one another to make a stable star. And there really isn't fission taking place inside the sun or other stars. It's really just a process of fusion. Okay, so you guys all got that. I don't want to dwell. Speaking of E equals mc squared, here we go. How does this equation work? So this is really the source of the sun's energy, is due to the fact that we are, whoops, that's not what I meant to do. I just meant to move this over so we can see. Okay. We are basically converting mass into energy. So I don't know how often you've encountered this equation, E equals mc squared, other than in pop culture. You've heard it being associated with Einstein. But if you think about what the equation actually means, the E stands for energy, the M stands for mass, and the C stands for speed of light. And the speed of light gets squared in this equation. Remember that the speed of light is 3 times 10 to the 8 meters per second. So when you square that, then you're getting a pretty large number, right? You've already got 10 to the 8, and then you're squaring it. So no matter what amount of mass you plug in here, you're going to produce a tremendous amount of energy, right? Even if I just plug the number 1 in here for 1 kilogram, then I've got 3 times 10 to the 8 squared joules of energy. That's a lot of energy. And that's just for 1 kilogram. And we've already said that the sun is a tremendously large, massive object, at least compared to the Earth. And so if we can convert that mass into energy, we're producing a lot of energy. It's usually not possible to directly convert mass into energy, but when you're talking about processes of fusion, then you can make use of this, and a small amount of the mass that is involved in the fusion reactions gets converted directly into energy. But we don't need a huge amount of that mass converted directly into energy because, as I just explained, it's going to add up to a lot of energy even if it's a small amount of the mass involved. Okay, so how does this fusion reaction take place? It's actually really an interesting process because when you think about it, what is fusion? Fusion is putting together of protons, essentially. Now, protons don't really want to be put together, right? Because they're both positively charged. And hopefully at some point you might have learned that opposites are going to attract when it comes to electrical charge. So, a positive charge and a negative charge, they might attract to one another, but the opposite is going to be the case for two like charges. If you've got positive and positive, they feel a force of repulsion between one another. And so they aren't really in the mood to get together. There's a force that's going to be resisting any attempt to bring two protons together. And so how is it possible then to stick a proton to another proton? It seems hopeless if you just look at the electric repulsive force between them. But what's going to happen is that when you have extremely high temperatures, these protons, and this is like one way of thinking about it, but the protons are almost moving so fast that they can't even engage that force of repulsion before they're stuck together. What's happening is that each proton has, you could imagine little hooks sticking off of them, there aren't really hooks sticking off of them, but let's just say that these hooks represent another force, which is very strong, even stronger than the electrical force, but it only engages at very close range. So if you can somehow manage to throw these things together, then their hooks can kind of attach, and now they're stuck together. That's called the strong nuclear force, and it's stronger than, as the name implies, the electrical force. But you've got to get those protons close enough together that their hooks can engage, or that force can engage. And in order to do that, you've got to have really high temperatures. In actuality, it's a little more complicated than that. If we look at the quantum physics picture, what's happening is actually quantum tunneling. And you know, I mentioned that the Bohr model of the atom is just an approximation because we can't pinpoint the exact location of the electrons. Well, it turns out that's true of any quantum particle. You can't tell exactly where the proton is, and because you have that uncertainty, there's a non-negligible probability that they're actually right on top of each other, and then they can fuse together. But you know, we don't need to go quite into that quantum picture. The high temperature explanation, I think, is probably a little more intuitive, and it's a close enough approximation for us to understand why these high temperatures are required in order for fusion reactions to take place. Once you get the two protons stuck together, then they're going to be stable because they're fused, and that strong nuclear force is going to bind them together. Okay? Now, we call this the proton-proton chain. Again, the whole step, every step of this is not going to be important for you to understand, but just the basic idea behind it and some of the byproducts that are produced is what you should think about. So you probably know that in chemistry you learned there are protons and there are also neutrons that can be in the nucleus of any atom. And so in a hydrogen atom, you basically just have one proton. That's it. Now, for a neutral hydrogen atom, you're going to have electrons buzzing around here, but it's so hot there that the electrons are kind of free to do whatever they want, and this is basically an ion that's roaming free. And we don't need to worry about the electrons for the purpose of understanding this fusion. So think of hydrogen as just a single proton. Then once you want to get to helium, where you've got, you know, two protons and two neutrons. And there's going to be a chain reaction that takes place to get you there. So if you start out with two hydrogen atoms, let's just say two hydrogen nuclei, i.e. two protons, through fusion, they can bind together to form an object that has two things in its nucleus. Now, why are they not both protons when I just said they're both protons? Well, in actuality, for a second, maybe they are, but what happens is then this other proton, one of the two protons, quickly becomes neutrally charged. Well, how can I go from being positively charged to neutral? In order to, there's something called conservation of charge. I can't just decide to become neutral once I'm positively charged. The only way I can do that is if I give off some of my charge somehow. And so what happens is that a positron is released so that I can change my charge into neutral. What is a positron and why is it different from a proton? Well, a positron is the size of an electron, only it's positively charged. Electrons are teeny tiny compared to protons. So it's not a proton because it's teeny tiny, but it's got that positive charge. So I've basically shed a little bit of mass in the form of this positron, and I've gotten rid of my positive charge so that I can become neutral. And for a long time, people thought that's all that was involved in this first step, that the two protons came together, you've got hydrogen 2 forming, where you've got a proton and a neutron, and a positron was released. But then they learned, actually, that's not all there is to it, because somehow we're not accounting for all the mass. The object that's left, a proton plus a neutron, if I add in the mass of the positron, I still come up a little bit short of what I started with, which was 2 protons. And conservation of mass tells me I can't just get rid of mass, right? It has to be converted or, changed to some other particle. I can't just make it go away. And so eventually it was discovered that a small amount of mass was also released in the form of something called a neutrino. The prefix here implies that it's a neutral particle. So I haven't changed the amount of charge I'm giving off. I'm giving off a neutral particle, but it has a little tiny amount of mass that accounts for that quote-unquote missing mass that I was looking for. So when this whole first process takes place, these two things are like byproducts of this first step, the neutrino and the positron. We're not really going to dwell on the positron, but we're going to get back to the neutrino in a little bit because it's actually a really interesting particle. Okay, so now I've got some particle or composite particle that's a proton plus a neutron. So you could think of it as heavy hydrogen. If one of these guys finds another single proton floating around, which is likely because the sun is made up of 71% hydrogen, then when these guys fuse together, now we will still keep the two protons and the neutron. So I'm not changing any particles, I'm not releasing any particles, but what I do release is a very high energetic light ray, a gamma ray. Okay, now we don't get gamma rays bombarded to us from the sun to Earth. By the time we get that light ray, it's going to have changed into visible or some other form. Some of them stay gamma rays, but most of them are going to change into something weaker and less energetic because, again, it takes 100,000 years to get out of the core of the sun. So in that process of bumping into one another, I'm going to lose energy. Okay, and by the time I reach the surface, I may not be a gamma ray anymore. But I start out that way. I start out as a gamma ray of light. Okay, so light is released. That's the important byproduct of step B. Then in step C, what the crucial thing is here is that if we've got this thing that's almost like helium, except that it's normal helium has two neutrons, and I only have one, but if one of these guys finds another one like it, then they're going to fuse together to give you that other, one of them is going to give you that other neutron, and then these other two protons will be free to fly off. And these two are important because now I can start this whole process over again, and it becomes a cycle. Okay? So in step A, we've got byproducts in the form of a neutrino and a positron. The neutrino is going to be interesting. Positron is just there. Then in step B, the important byproduct is the light that we get from the sun. And then in step C, the important byproducts are that we get two more hydrogen atoms so that we can start the process over again. And you may be wondering, well, wait a second, how could I have given these things off and now I have the same amount that I started with? That doesn't seem possible. But remember that other characters entered the storyline here, right? I started out with two hydrogen, but then here another hydrogen entered the story from somewhere else. And then I had helium-3 here, but then another helium-3 entered the story from somewhere else. So I did bring in more mass. I'm not ending up with the same amount or somehow more mass than I started with. These things were given off in the process, but it all balances out. Okay, so I promised that I was going to talk about neutrinos and why they're interesting. So, like I said, for a long time, it wasn't really understood that neutrinos would be given off in any part of this process or even what a neutrino was. Once the neutrino was discovered and it was understood that they should be produced in the nuclear reactions within the sun, then people set about trying to detect them. But the problem is that neutrinos are extremely hard to detect. The reason for that is that unlike photons, which remember, they're trying to make it from the core to the surface of the sun, and they're bumping into everything, losing energy along the way, taking 100,000 years just to make it from the core to the surface of the sun. Neutrinos aren't like that. They actually are able to just pass through things practically undeterred. You can have layers of lead, and a neutrino can pass straight through it, unperturbed. You probably have had neutrinos stream right through your body and didn't even know it. But because they can make it through things so easily without interacting with other particles and other masses, that makes it really difficult to detect them. Okay? Those neutrinos can make it from the core of the sun to the surface of the sun almost immediately, whereas it takes photons 100,000 years. And then 8 minutes from then, they make it to the Earth. But how are we going to detect them if they can just pass through everything, right? It's like trying to catch a bullet with tissue paper or something. It's just going to make its way right through. How are we going to do this? So what you need is you need to recognize that you're only going to be able to catch a very small portion of them. And if you're able to catch them, if you're lucky enough, you're going to want something huge in size to maximize the numbers that you're going to be able to detect. And so neutrino detectors were built really massively in the hopes of detecting a small fraction of the neutrinos produced in the sun. And it was figured out, well, what fraction or how many neutrinos should I realistically be able to, you could calculate the odds and figure out how many I should be able to detect. And if I'm able to detect these things, then it's confirming that I actually do know what's happening with those fusion reactions inside the sun. Okay, because my theoretical model is that, this proton-proton chain where neutrinos are produced. If that theoretical model is correct, then I should be able to detect some of these neutrinos, a small portion of them that I've been able to calculate how many. And, I set up my neutrino detector to maximize for that, and then I'm going to count how many detections I get. Okay? So, people did this, but around the turn of this century, it was understood that we're not detecting nearly as many neutrinos. Did you have a question? Yeah.
Like, do they do anything when they're like on the Earth, or is it really just to like confirm like the measurements?
Yeah, they don't really do much of anything to the Earth. Like I said, because they're so impervious to matter, they're just they just fly right through. I'm not a biologist, but it's possible that maybe that could do damage to our cells, maybe. But I don't really know that for a fact. I do know that when certain charged particles interact with cells, they produce free radicals, and that can drive cancers and such. I don't know if neutrinos are among those things, but it's possible. I think for the most part, though, they just kind of just fly through everything. It's a good question. But the problem was that when people started trying to look for the neutrinos, they were like, we're not detecting nearly as many as we should. Why is that? Are we misunderstanding this model, this idea of how the proton-proton chain takes place? Or is there, something weird about neutrinos that I don't understand? Okay? And so those were kind of the two rough possibilities that, either there's something wrong with how I understand the fusion reactions in the sun, or there's something wrong with how I understand neutrinos. And so to understand that, we've got to ask, well, what again is a neutrino? I already mentioned that they're very small in mass, that they are neutral in charge. But they're also, you don't need to know a whole lot about particle physics or, a lot of this you don't need to commit to memory. But in particle physics, there's something in addition to charge, which is called flavor. Believe it or not. It's kind of funny, but it's called flavor. And it turns out that neutrinos come in 3 different flavors. So you can think about this like Neapolitan ice cream if you want, or something. Chocolate, vanilla, strawberry. It doesn't really matter what they are. In actuality, they're termed electron, muon, and tau neutrinos. But you can just think of them as chocolate, vanilla, and strawberry if you want. Doesn't matter. And what we knew is that in the sun, we don't need to really go through all of this, I guess. In the sun, only one of those 3 flavors was predicted to be produced. So let's say that neutrinos can exist in chocolate, vanilla, and strawberry, but the sun's fusion reactions only produces vanilla neutrinos. And so when I make my particle detector, here's one of the first particle detectors ever made. It was made deep within a mine. They put these underground so that the detectors are not confused by other charged particles that might be streaming from outer space, because neutrinos can make it underground, whereas the other stuff, not so much. So this way you should only be getting the neutrinos. In any case, This one was built in 1968, and then later in the 1990s, there was Super Kamiokande, and that was an even larger neutrino detector. And both of these neutrino detectors at first were just looking for vanilla neutrinos. Okay, I'm calling them vanilla. It wasn't really vanilla, but they're only looking for one of 3 flavors. That's all they're looking for. And so that was the thing that they were missing, is that you only have about 1/3 of the neutrinos that you expect, but you're only looking for one flavor. So people thought, again, 2 possibilities. Either we misunderstand the proton-proton fusion reactions inside the sun, or maybe we misunderstand something about neutrinos. Since there are 3 flavors of neutrinos and I'm only getting about 1/3 of what I expect, is it somehow possible that this vanilla flavor that's produced in the sun could somehow morph into the other 2 flavors? And since I'm only looking for 1/3 of them, I only get 1/3 of them. Okay? And so what they did is they created another neutrino detector right around, again, the turn of the century in, I believe this was Canada, Ontario, the Sudbury neutrino detector, which is really large, again, just as the others were. And this neutrino detector was able to detect all 3 flavors of neutrinos. So this was to test the hypothesis that, well, maybe somehow the neutrinos are changing flavor between when they leave the sun and when we detect them. And within a short amount of time, just a couple years, they were able to confirm that, if you account for all 3 flavors of neutrinos, we're getting exactly the amount of neutrinos we expect to get from the sun. Okay, so this revealed 2 things. One, it revealed that our understanding of the fusion reactions inside the sun is actually correct, because we're getting the correct amount of neutrinos. And then it also revealed that neutrinos have this weird thing about them where they're able to change flavors. We call this neutrino oscillation, is the buzzword. But you could almost think of it as just morphing. Like, think of them as Raven. She can change, X-Men. Anybody know what I'm talking about? Oh my gosh. All right, so let's go with Star Wars. A changeling? No? Nobody? All right, well, just imagine some mythical being that can change forms. Okay, so you start out as a human and then you morph into a centaur or something. And so this is basically what neutrinos can do. And if you account for all of your 3 identities, then you can find all the neutrinos that you need. Okay, so I've dwelled a little bit on neutrinos, but let's take a look here at this clicker question, which again has more to do with the fusion reactions than the neutrinos. Whoops, hopefully I didn't give that away. Don't overthink it. All right, we all in? All right, so everybody said answer B. Yay! We all got it right again. Again, you didn't need to overthink this. The correct answer is the fusion. Again, those neutrinos are kind of proof that that fusion is taking place. An interesting note historically is that when people came to understand how old the Earth actually was, like when they found really old fossils and they're like, oh, wow, the Earth's actually billions of years old, then people were like, well, if the Earth is billions of years old, then the sun presumably is at least as old. And so how is it still shining? You know, in those days, people didn't understand this idea of fusion. They were like, what source of energy could keep going for that long? And so some people tried to calculate, well, if you had such and such amount of mass and it was burning like coal burns, how long could it last? Or if it was, you know, a fission reaction, how long could it last? And none of these things could sustain that amount of energy for that long. And so, you know, fusion kind of had to be at work here in order to keep that going for as long as the sun's been around. And again, the sun's only about halfway through its lifespan, so it's going to keep doing that for another 5 billion years. Anyhow, moving on. So, you know, I talked about the surface of the sun in terms of these granules that you see in the photosphere. But one of the other features that I glossed over were these sunspots. Okay, and these sunspots were first noticed by Galileo, since he was the first one to turn a telescope towards the heavens. Again, he didn't invent the telescope, but he used it for that purpose for the first time. And looking at these, you really shouldn't look directly at the sun, but Galileo, I guess, didn't know that. And looking at the surface of the sun, he saw that there were these dark spots on it, sunspots. And, you know, they look a little strange. What is causing them? It's kind of a complicated effect known as the Zeeman effect, but you can just loosely think of it as oddities in the magnetic field that's produced by the sun. So, you know, the Earth has a magnetic field, as you may or may not realize. That's how we can use compasses to point towards north. The sun also has a magnetic field, and it turns out that that magnetic field kind of twists and turns and can produce strange effects that result in these sunspots. They're actually cooler regions here where it's dark. And so you can think of those magnetic fields as, you can imagine them being lines. They're not really lines like this, but you can picture them as such. And so a charged particle is going to spiral along these lines. And when that happens, if it's kinked in some way, you can get something that looks like this as a result. And here's the temperature look of it, where here we've got a cooler region, and then hotter regions underneath and around the outside. Okay, and then if those kinks bulge out in the magnetic field, you can get some strange U shape like this, where hot gas, I mean, they're saying cool gas. It's hot because it's the surface of the sun, but it's cooler than the rest of the surface, and so it's getting trapped in these magnetic field lines and producing this thing that looks, we call it prominence, but it kind of just looks like a U shape. I like to think of this as, you ever have a spiral bound notebook and then some part of it gets like really kinked larger, and then it's annoying, drives me nuts. But anyway, that's sort of like what's happening. The lines should be all nice and neat, but one might be kinked up higher, and so you end up with this U shape. And these things are unstable, as you might suspect, and you know, a prominence then can result in a coronal mass ejection if one of these ends lets loose and all of that matter flies off into space. And this is really large, by the way. Here's the Earth, you know, to give you a sense of scale here. Here's the Earth in relation to the size of that prominence, really large in size. Let me see how we're doing time-wise here. I think we can probably get through this, so let me go back to where I was. Okay, I think we'll delay the break until we finish this. We should have enough time for this activity, and then we might be able to get into stars as well. But let's, for now, move on. Okay, move this thing again. I already mentioned solar flares, basically eruptions of hot gas and radiation, and this is generically what we call space weather because it can affect our satellite communications, because all of these mass ejections and flares send charged particles and energy out into outer space, and then when it reaches the Earth, these little satellites that are orbiting the Earth can be susceptible to interference from these flares or these ejections. Here's a picture of a coronal mass ejection about to take place. Look at how huge that is. I mean, this is the whole sun. Obviously, this is not as dense as the sun, but, you know, that's a large piece of matter that's coming off of the sun. And what's interesting is that our sun is relatively non-active as far as stars go. Some stars are even more active and are ejecting matter even greater than the sun is. When you have a coronal mass ejection, in addition to potentially interfering with satellite communications, another thing that can occur is that the charged particles in the matter that's being ejected can interact with the Earth's magnetic field. So we've talked a little bit about the sun's magnetic field, but I mentioned that the Earth also has a magnetic field. And the Earth's magnetic field is directed so that, you know, the North Pole is one pole of the magnetic field, and the South Pole is another pole of the magnetic field. And the magnetic field lines kind of go like this, okay? And they're more densely spaced near the polar regions. So those charged particles that get trapped in a spiral, they get more trapped in the spiral towards the polar regions and that's the only place they can really plummet in towards the Earth's atmosphere. And so near the polar regions, those charged particles can then interact with the atmosphere and produce a glowing effect. We call this the northern lights. Presumably, if we were in the southern hemisphere, we'd call them the southern lights. You can generically refer to them as the borealis, aurora borealis. Actually, what does borealis mean? Maybe it's just the aurora. I feel like one of those probably is north and one of them is pole. I don't know. Anybody know? Aurora? Anyway, it's this glowing effect that you can see near northern latitudes or southern latitudes. It's usually not visible here in western Pennsylvania, but occasionally you can see the northern lights here. But since it's Pittsburgh, chances are if the northern lights are visible, then it will be cloudy and you won't see them anyway. So I think that happened like last time the northern lights were supposed to be visible. It was like totally cloudy and you couldn't see a thing. But in any case, what it is these charged particles interacting with the Earth's atmosphere and the gases that are there. Now, there's also a cycle to the prevalence of the spots on the sun. So, you know, I mentioned it has to do with the magnetic field lines, and, you know, that's true, but it turns out that there are more or less active times where the magnetic field gets these effects more than others, and you see more spots on the sun during some periods of time than others. And it turns out to be a rough cycle. Roughly every 11 years, we're going to get a peak. And so this graph kind of depicts that, going back to, you know, Civil War era up through about 2010. And you see that the size of the peak may not be the same. Like here in 1960, it was really large, whereas let's say here around early 20th century, it was kind of not quite as large. But nevertheless, there is a peak pretty predictably every 11 years or so. And, you know, that's just what we call the solar cycle. And so there will be times when you have more or less space weather, so to speak. And so to understand this a little bit better, when you have these sunspots occurring, you know, here maybe they're neatly lined up, but the sun is not all rotating at the same speed, which is weird, right? We're used to the Earth where, you know, we all spin around and it's 24 hours till the next day. It's a solid object like a ball that's spinning. But the sun is a ball of gas. So rather than all spinning at the same rate, the stuff that's near the equator is actually going to spin faster than the stuff that's near the poles. And so you see here that if you're near the poles, it might take you a month to rotate around once, whereas if you're near the equator, then you're talking more like 25 days. And so that's going to warp things slightly differently as time goes on. This type of rotation where you're not rotating all the same speed is known as differential rotation. The gas giant planets also have some amount of differential rotation also, because they, like the sun, are made primarily of gas. Okay, here's another clicker question. Oops. Okay, I think we're all in. And so everybody says D. I think that's right. I've covered it up. A, B, C, D. Yes. Sorry, it said 4, so I was like, wait, what? But you figured it out. Hopefully your remotes say numbers and letters, do they? Okay, so yeah, so every 11 years is the correct answer here, as I mentioned just the slide before. Not quite a decade, but very close. And I guess that concludes this particular lecture. So the next thing we're going to do is this activity, but let me stop this recording.